Good day, everyone. Today's presentation is on ETAP 21, Digital Continuity Design to Operate. For part one of this webinar series, we are going to cover today, starting from the top right, model and visualize, design and analyze, and then for part two of this webinar, we are going to talk about monitor and predict, operate and optimize, automate and control. So essentially, the foundation for the monitor, predict, and what we know as the ETAP digital twin, the foundation is we're going to cover today, which is the design and analyze modules, as well as creating the model and visualizing the model, the different tools available for that, and the different design and analysis modules for performing power system studies. The materials, the items that we're going to cover today are at the core. They're the foundation of ETAP's unique and innovative digital twin solution. So with that, I'll start with a little bit of background on the three-dimensional ETAP's three-dimensional database. Again, it's at the core of the foundation for digital twin. The ability of being able to handle multiple operating conditions and what-if scenarios is at the core of ETAP. And more importantly, at the core of all analysis modules such as arc flash, right? When we're doing an arc flash study, for example, we must consider multiple operating conditions into account. So that's where the three-dimensional database in ETAP 21 has been enhanced, and it has always been a powerful feature for the software. But as I would show, it has greatly there have been great enhancements on ETAP 21. So moving on with some of the new solutions, features, and capabilities. It's a very safe release, making all the right moves to improve safety. It's reliable, efficient, compliant, and most importantly, sustainable. As we will see, creating some models to be used on renewable and new greenfield projects. It's really going to change the energy landscape. As I mentioned, at the core of the three-dimensional database, there's also safety modules such as arc flash. New modules are smart inverters and its modes of operation for grid code compliance. Transmission line ampacity as per IEEE 738 standard, and also new French standard PE and shock calculations for cable sizing. Again, this is just a quick highlights of the new enhancements and new capabilities. We will go into details here as part of this presentation. Also enhanced reliability assessment, switching sequence management, and time domain load flow. So as you could see, some of the distribution type modules for power system analysis greatly enhanced. Also enhanced our Transient Stability module, distance protection, and the StarZ library. Also enhanced is the ability to visualize a single line diagram, not just on the logical representation that we're all very used to seeing, but also in the ability to display that information in a geographical network. And also, as we'll cover, the ability to import from Esri and other databases such as Windmill and Sine. We'll cover that as well. Increased design speed and accuracy for ETAP Python for scripting and automation. The enhancement on a lot of the data exchange utilities, as I mentioned earlier, Windmill, SKM, ETSA being a brand new data exchange utility, and ETAP API as well for those users who require an API. Also enhanced. And these modules here are actually going to be covered on part number 2 of the ETAP 21 release series. These are more on monitoring, control, training and operational awareness. And the modules that will be covered on part 2 are Operator Training Simulator, Automated Fault Analysis System, or ETAP AFAS, Fault Location, Isolation, and System Restoration, FLISR. Also, modules that will be covered in part number 2 are Asset Management with Advanced Protection Analysis, which is ETAP Situation Intelligent, Asset Management, VolVAR Optimization, which is part of ETAP's ADMS. And also on part number 2 are Audit Management, OMS, Distributed Renewable Management, ETAP DERMS, User-Defined Reports for users that are currently using ETAP SCADA. Power System Management and Control Renewable Systems that have been enhanced in ETAP 21, Microgrid Controllers, and Power Plant Controller as well. Increased design and speed and accuracy for the eProtect, which is an online protection and asset management, eWeb, web-based visualization and management, and the ETAP data collection app, the field data collection app, which will be the beginning of the features. So with that, I'm going to pass it over to you, John.
Thank you, Victor. We've also released a new version of our ETAP app. This app is used for mobile field data collection and verification and is now released on Google Play. So historically, we've had it on the Apple Store and Microsoft. Now, if you have a Droid tablet, you can download the ETAP app as well. We've had numerous feature enhancements for the one-line diagram. Our intelligent single-line diagram now allows you to modify devices directly on the single line. You can change the themes for any meters you have in the project. And the information, if it's misaligned, you have easy alignment tools from the right-click menu that allow you to clean up the model and align any set of information center, left, right, and vertically spaced so that you can efficiently and quickly clean up the annotations on your one-line diagram. So directly here, we can retype the device ID, or you can paste it from a clipboard. Now you no longer have to go into the device editor, double click, and change the ID. This can be done directly on the one-line diagram. And if you have overlap from your annotations and results, you can right click and quickly toggle positions so that they can adjust the location and you can clean up your model extremely quickly and efficiently. Researchers from various countries have made significant contributions to the development of more accurate and conservative incident energy calculations. In Australia, the Sweeting method led the way by providing what many ACFlash experts consider the predecessor model to IEEE 1584-2018. The Sweeting method, as published in the Australian Electrical Safety Standard, provided more conservative results than IEEE 1584-2002 for many years, until 2018 standard was released. Now Sweeting method remains as a very reasonable method still in use in several countries and utilities in Australia and around the world. This method has been implemented in ETAP 21 in the form of a calculator, which has user-friendly typical input parameters, includes considerations for the thermal energy and melting properties of different conductors, like copper and aluminum, and also provides several plots and easy-to-use intuitive interface features, which makes what-if scenarios very easy to execute. Additional features include export results to CSV in Excel, or batch import and export for thousands of locations in an instance, ArcFlash custom label generation, and PPE evaluation based on NFPA or user-defined levels. So with this ArcFlash calculator, you can quickly drag the fault current, and dynamically the results will update for minimum incident energy results or maximum incident energy results. And we're comparing these results against NFPA 2018, or you can user-define your category levels as well. Selecting between different conductor materials, and at the end, we can batch import, so you can select Excel file with data from multiple locations From here, we process the information and we calculate all the results. So 31 entries have been processed and calculated. And at this point, it's very easy to generate labels for all of these locations. So we select Australian labels that are provided by default, quickly generate the label, and your arc flash calculations are performed for the Australian standard. Just like with our Australian counterpart, the German Electrical Accident Insurance Institute has updated their standard with two methods for calculating arc flash and direct current systems. For those of you familiar with ETAP's DC arc flash module, you will find that their new methods are somewhat like our maximum power method and Stokes and Openlander methods. The worst case method is a spin-off of the maximum power method, but is expected to be just as conservative, if not more. The iterative method implements different anode and cathode and arc voltage gradient coefficients. The existing German arc flash calculator includes a new tab for DC arc flash analysis for both series and shunt faults, which can be extended to thousands of locations by means of batch instruction files. Just like its Australian arc flash evaluation tool counterpart, the German DC arc flash calculator includes standard-specific arc flash labels. This tool also includes nice features to improve productivity and reduce the data entry time. The German standard does not follow NFPA 70E PPE requirements, but follows instead IEC PPE standards like VDE 0682306-1-2. The tool also includes plots and reporting features to send results to Excel. One notable item about the German DC arc flash calculations as implemented by ETAP is that our program also provides incident energy results instead of just simply arc energy results. This can and will prove tremendously useful when you try to correlate DC arc flash results obtained with the German arc flash calculator with those obtained using the ANSI, IEEE, and FPA methods. This feature makes ETAP implementation of this German DC arc flash standard superior to any other options out there. So within the calculator, you can go to the DC arc flash tab and you have your two methods, worst case or iterative, as we previously described, and then the shunt and series fault type options. And as you change them, the results are dynamically updated, as is with any of the sliders for voltage, current, working distance, gap ID. We can dynamically change any of the input parameters for quick results. And we can look at plots as well. So with the Australian or German arc flash calculator, we can dynamically change the input parameters and quickly see how it affects from a plot perspective. Up to today, all arc flash standards provide examples of incident energy calculations only using constant symmetrical RMS voltage short circuit currents. Of course, IEEE 1584-2018 makes mention that systems with decaying short circuit current are likely and should be considered, but provide no clear methods to evaluate the incident energy as a function of time for such systems. ETAP arc flash has had a decay method in place which has been used for over a decade with great success. However, in version 21, a more accurate method has been introduced to allow engineers greater flexibility in determining the incident energy using transient short circuit currents. The onset of microgrids and DERs make it much more important to have more accurate methods to deal with islanded short circuit sources. This new feature allows the users to specify the time constants and X/R content of the bolted fault current and conservatively includes such effects for systems for which these parameters have significant effect. We are aware that the IEEE 1584-2018 method does not contain a clear way to specify the limits of system X/R. This tool can be used to account for this effect for systems with unusually high X/R ratios. Furthermore, the generator could decay quite quickly for some generator excitation systems, such as static excitation system. This solution allows the engineer to model such decay and consider its effect in the overall integration of the final incident energy. Transient arc flash plots are provided and are fully customizable and include the ability to render in both 2D and 3D form. The very nice aspect of this customization is that a user can create a template and save it for future use. These templates are transferable to future projects and can be reused in future versions of the software. The transient arc flash plots take advantage of a new concept called plot view snapshots. Now you can have unlimited one-line diagrams, unlimited data revisions, unlimited configurations, and the configurations are protected by switching modes, and now unlimited ways to show in different saved plots. So we fault a bus at the generator. We can run IEC 61363 for our results. And when you open the bus editor, we can pull up the calculator directly. And within PlotView, you'll see the transient arc flash method plots and all the input data that you can associate for the transient arc flash calculation. Now we can select the results ran for IEC 363 or input them directly in the calculator itself. Here I'm selecting from the short circuit study we ran. We have our plot views for the results, and this is provided from the study for the input data and the results calculated from our transient arc flash calculation. Transient signal analysis can be very difficult, even for engineers with many years of experience. ETAP 21 includes a new set of features which allow the engineer to detect the type of signal performance from their dynamic system study. The Scope Signal Analyzer can detect the feedback control loop performance by automatically viewing and analyzing all the desired signals to detect potentially troubling behavior which cannot be easily seen with basic alerts. The rate of change and correction rate plus the controller damping power are all graphically analyzed by the Signal Analyzer. On top of this, the Signal Analyzer can automatically review your transient stability results and flag conditions of potential lack of stability, like rotor angle swing violations, under voltage, under frequency limit violations, and several others. This solution even allows you to compare automatically motor starting and transient stability motor acceleration plots and flag which locations do not meet the minimum starting voltage criteria, or even which motors potentially fail to start. This solution adds another alternative to the rich ETAP family of plot analysis solutions. The Scope Signal Analyzer also allows you to record or create lists of special plots of interest so that every time you rerun a complete study, you can bring the same plots aligned to the same settings with your specific level of personalization. The new concept of plot view signal analysis snapshots will revolutionize the way we manage, print, and create output reports for your projects. When selecting and loading the Scope View Analyzer plots, you can right-click and customize each plot and save this theme for use in any future analysis. The Scope View Analyzer is at the top toolbar. We can browse and select the saved plots. We import specific studies that we want to run, in this case transient stability and motor starting. You can use default plot views, or you can load your snapshot of your created plot settings, select the snapshots, and utilize saved themes for your analysis. In ETAP 20.6, we introduced a much-awaited feature, which was the CT saturation analysis. ETAP 21 has a great enhancement by allowing users to export all saturation results to Excel for further plot customization or for further analysis and reporting. The AS3008 and NZS3008 method is based on Australia-New Zealand standard for electrical installation selection of cables. When AS3008 is selected from the standard dropdown, this method is based on part 1.1 of the standard cables for alternating voltage up to and including 0.6 to 1 kV, typical Australia installation conditions. When NZS 3008 is selected, the method is based on part 1.2 of the standard cables for alternating voltages up to and including 0.6 to 1 kV, typical New Zealand installation conditions. This standard, including part 1.1 and part 1.2, applies to several types of installations, including above ground and underground configurations. This can also be used for unarmored single core or multiple core cables with nominal voltage up to and including 1000 volts AC. So for many of us who are familiar with the cable editor and the cable sizing within ETAP and cable Ampacity, we can go right into the capacity page, select the applicable standard, whether that's Australia or New Zealand now, select your installation type, and ETAP automatically calculates the derated values. Now you can change the size directly from the editor and look at your new results, or from the sizing tab, we can select optimal size provided or one size smaller. And this is provided based on the constraints selected. So you have multiple constraints that you can apply, and once applied, the size will update to keep you within the required objectives. We've also expanded upon our ETAP Python scripting. Now Python scripting includes automation for short circuit calculations and protective device sequence of operation as well. And with that, I'd like to pass this back to Victor so he can continue with many more features from ETAP 21.
Thank you, John. And now let's go over visualization enhancements. First, let's begin with Geographical Network or GIS view. For those of you who are familiar, currently using ETAP, you're very familiar with the graphical representation of a single line diagram, which I am displaying here on the left hand side. So this is typically the logical representation of your single line diagram. It contains protected devices. Protection engineer uses it for protection coordination studies. You use this typically for doing arc flash or circuit studies and visualizing all the results. It gives you a great logical view of how the system is organized. However, for distribution and even some oil and gas users who require the ability to visualize over large geographic areas, GIS is available. As you could see over on the right hand side, we are zooming into different parcels, and we can begin to see the overhead lines in blue and down to the individual. In this case, it appears to be residential loads, yes, but that could also be, for example, oil wells and other loads that happen to be on a large geographic area. So the single line diagram that you see on the right hand side, the GIS view, that's actually generated by importing the data from an existing database such as Esri, or from other models such as SIME or Windmill, or multiple other GIS databases such as ArcFM. Continuing with new enhancements and capabilities, smart inverters ensure grid code compliance and stability with smart inverter modeling and simulation. You're able to simulate impact of utilizing smart inverters to ensure grid stability and reliability with DERs. Also includes multiple modes of operation such as volt var, volt watt, and watt power factor. Ability to use user-defined control curves or static var support, real or reactive power priority modes, consider and include smart inverter constraints, and meet requirements and verify compliance as per IEEE 1547 and California Rule 21. Improvements on transient stability or frequency calculation for grid forming inverter, improved frequency estimation algorithm for dynamic simulation. For STAR-Z and distance relay library, gain insight into line protection, relay performance, and evaluate system-wide protected device operation. Simulate protection impact based on unbalanced faults. STAR-Z also integrates with eTrax for railway system protection simulation. Improved line protection library with user-defined comparator, digital source stencil, quick set frequency option for operating and restraint signal list of amplitude comparator. As mentioned earlier, ETAP 21 has a strong applications for distribution. which means reliability assessment has also been enhanced, assess the availability and the quality of power supply at each customer service entrance, analyze complete systems or targeted feeders only, display assessment results directly on the GIS view or single line diagram, and enhance plot selection with indices such as CATI, SATI, SAFI. Now for switching optimization, automatically determine the optimal system configuration to achieve user-specified objectives. The objectives can be selected from the switching optimization study case. So as you could say, minimize losses, feeder balancing, optimize voltage. And after we run, we could see the visual alerts displayed right on ETAP One-Line Diagram and GIS view. Also enhance modeling for switch capacitor banks. So after running this simulation, we could see that there are 3 switching locations. The ETAP is suggesting to keep open for maximum feeder capacity. Enhancement to switching sequence management, or SSM, ensures safety by graphically building, simulating, and validating switching sequence plans. Here's the SSM interface. It allows us to validate of switching plans using unbalanced power flow, simulate switching plans on one-line diagram or GIS view. You can then export the sequence plans to Microsoft Excel and export plans to online sequence management viewer and utilize during system design or operation. So I went ahead and stepped through a particular switching sequence, and ETAP would provide you with information if there are any overload conditions as well as over/under voltage conditions. Time domain power flow or time domain load flow allows for automatically and sequentially vary load and generation to solve steady state power flows over time. ETAP 21 is able to perform quasi-static load flow with controller dynamic simulation. So going over to the time domain load flow study mode and selecting from the study case quasi-dynamic model simulation in time domain analysis. Also the ability to model smart inverter simulations and analysis, time domain profiles for VFD, induction and synchronous machines, and a graphical plot for intelligent controller and SVC StatCom. I will now show you a quick example where this is a sample PV. So as you could see, this is how the time domain load flow is able to get multiple input data. In this particular example, I have data coming in from the PV source as hourly. So as you could see, in the early or late hours of the night, there is no generation. And as we begin to advance throughout the day, you begin to see how a real reactive power factor and other factors begin to be considered. You also have the ability for a column based on irradiance, and the time frame you could make it on a minute basis, hourly basis, weekly basis, and the same thing can be performed as well for loads. So this is a varying real and reactive power of how this particular load is consuming the energy. Other enhancements to time domain power flow are total active and reactive power plots, time slider and alerts for GIS diagram, interpolation between time steps smaller than profile resolution, and high resolution time step external data support and simulation. So after running a time domain power flow simulation, I would like to go ahead and display my plot analyzer and see how the voltage profile is doing for this particular PV installation. So bringing up my plot analyzer, you could quickly see that the voltage over an hourly period throughout multiple days, right? Starting from January 1st all the way through January 7th. Again, as I showed you earlier, this is on a hourly basis, but if you have historical data that's taken on a minute basis or even on a second basis, you can certainly specify a much tighter resolution that way. For line ampacity calculations, calculate the current temperature characteristics for overhead lines. It now complies with IEEE 738 standard, study conductor ampacity versus temperature characteristics, and consider effects and adjustments due to weather, solar heat, and geographic local effects. For those of you who have the need to import from third-party software and want to accelerate digitization and data exchange through built-in conversions, the SKM import utility greatly enhanced. It has now built-in conversion for DC systems and also an improved automatic single-line diagram generation. Also, a brand new module is the ability to import from Power Analytics ETSA into ETAP. It automatically will generate a single-line diagram. And again, as I mentioned earlier, for those of you who are looking to take advantage of accelerating digitization and data exchange through built-in conversion, this will save you many man-hours on trying to import a file. Not to mention, it provides you with now the ability to take advantage of other applications such as predictive power system analysis and essentially bring in real-time data as your initial running conditions for studies such as short circuit analysis, arc flash, protection and coordination, motor acceleration, essentially providing you with the ability to migrate over into a true digital twin application. Quickly to go over where these data exchange utilities are found, go from the edit menu, make sure you're on the edit menu. Under the data exchange pull down menu, you'll see all of the available import capabilities. So as I mentioned earlier, the ability to import from SIME, which requires GIS, is there. Import from Palladium Design Base, formerly ETSA. Import from Easy Power, and also import from SKM. There's also the ability to import and export Revit, and there's also the ability to import from AutoCAD Electrical. For EPCs and more industrial users, Aviva Electrical and Aviva Engineering, as well as Smart Plant Electrical, is supported. And finally, the ETAP application or baseline has been improved compatibility and security compliance. So for those of you who are on 4K or even higher resolution displays, now supported. More responsive and performance improvements throughout. Username access, role display on the application title, and also copy text box to clipboard for other applications. And with that, I'm going to pass this back to John for the conclusion.
Thank you again for watching our ETAP 21 release highlights, Part 1, focused on new and enhanced solutions for design, analysis, and simulation of your power system. Don't forget to watch Part 2. Part 2 focuses on the highlights for monitoring, control, automation, and management. This includes new solutions for our operator training simulator, predictive simulation, our digital twin-driven automation and renewable energy power management system, and eProtect, our relay protection and asset management system. Thank you again, and we look forward to seeing you for Part 2 of our ETAP 21 release highlights.